So today we're going to talk about finding the limits of slightly more complicated functions. And we're going to go over a bunch. So we're going to try and go through some of these step by step. And a lot of it boils down to, I can't find it normally. Normally, you just be able to take the number, plug it in for an algebraic one. But some of them are more complicated, and it does pay to sort of fix it up before you try and do it. Hey, Andrew, we're just getting started, so you're right on time. So with one like this, if you notice, you try and plug in 8, and what ends up happening is you get 0 over 0, right? And you can't do that, right? You can't do 0 over 0. That doesn't work. So we're going to have to play around with this a little bit before we get in. And in your Algebra 2 class and in your pre-calc class a little bit, hopefully they talked about factoring. So the top you can't do anything with, but 9 times out of 10, the top is going to be a key. If there's something you can do, then this will give you the hint. X squared minus 64, that's a difference of squares, right? X squared minus 8 squared. So you can actually factor that into x minus 8, x plus 8. And now you've got a factor that cancels on top and on bottom like this. And what you're left with is 1 over x plus 8. And don't forget to bring that limit along with. And now that we've gotten rid of the discontinuity that's keeping us from doing this, look at what happens when I plug it in. 1 over 8 plus 8. 1 over 16. So the purpose of, since we're doing this limit, what we can do is we can just sort of hold out, say, okay, well, it didn't work. Let's see if I can get rid of that hole that's in there, and then ta-da, here's our answer, 1 over 16. Does that make sense? It's just factor, cancel, plug in. Let's do another one. So with this one, as we're going, again, we try and plug in 4. We're going to end up with 0 over 0. And we don't want that. We want to actually get an answer if we can. So we're going to simplify this fraction up here, get a common denominator, right? There, this has a v, this has a 4. So let's give the rest of the factors to it. This one's missing the 4. And this one's missing the v. So we're going to put a 4 on top and on bottom here, a v on top and on bottom here. And then we're going to simplify, right? 4 minus v over 4v, all divided by v minus 4. And remember, when you have a denominator inside of a denominator, you can take this denominator and bring it down to the bottom like that. So what this really is 4 minus v, and then you've got 4v times v minus 4. Now, here's the thing I want to point out real quick, is that these look very, very close to each other. It's just they're backwards, right? When you've got 4 minus v and v minus 4, they're the same thing, just different by a factor of -1. So just like in the last problem, where you had the x minus 8 and the x minus 8 that you canceled out and we're left with 1, you're going to do the exact same thing here, but since they're backwards from each other, you're left with -1. So what I'm going to do is I'm going to rewrite this as limit as v goes to 4 of -1 over 4v. Well, now I don't have to worry about plugging in 4 and getting 0 on the bottom anymore. So I can just plug it in. And what does that end up being? negative 1 over 4 times 4, which is 16. Y'all see what I'm saying? So here, with this one, we got to do some fraction action, and we got to turn this into a single fraction. So we find the common denominator, and then we can bring this part down to the bottom, cancel, and then actually plug in now that we don't have to worry about that hole anymore. Okay, what else do we have here? Same idea here with this one. There's a hole on the bottom. If I try and plug in 2, I get 0 over 0 again, and I don't want that. So what we can do is we can factor out the top and factor out the bottom. And notice how I'm putting an arrow here instead of an equal sign. I don't know if you're noticing that I'm putting arrows here instead of equal signs. And the reason I'm putting an arrow in for that first step is because I always have to bring this limit along with, and here I'm just doing some thinking. On the AP exam, if you put an equal sign somewhere, it has to be an exactly equal statement that you put on the other side. So when in doubt, arrows are almost always better, actually. If you have arrows, they know not to mark it wrong if you're just sort of thinking with your hand on the paper. But if you have an equal sign, sometimes they won't like that. So when in doubt, arrows are great. So you can factor this out. These are a difference of squares because the square root of u to the 4th is u squared. So u squared plus 4, u squared minus 4. And then you can break this one down because this is still a difference of squares. We got u squared plus 4 times u plus the square root of 4 is 2, and then u minus 2. And then this one down here, this is a difference of cubes, and there's a special formula for that. And I'll show you. It's the hardest thing to remember is I'm going to show you the formula here just so you have it. And I'm specifically doing this without all the signs on purpose for a good reason. And I'm going to tell you that now. So the thing of it is, the rule, the way that it goes, this is the formula for expanding it. And then with the signs, it always goes same sign as whatever this is, opposite sign of whatever this is, and positive. So if this is a minus sign, minus, plus, plus. If it was a plus sign, it would go plus, minus, plus. Same, opposite, positive. If you can store UV, U squared, UV, U squared somewhere deep in the recesses of your mind, and then same, opposite, positive, you won't have to memorize this whole godforsaken thing on its own. This is the trick that I always used, and it has meant that I didn't have to sort of bleed out my ears when I was doing this. If you can remember this part, and then remember the signs separately, it'll keep you from having this gigantic problem in your brain. So 8 is 2 cubed. So that's why it's a difference of cubes, right? 8 is 2 cubed. So u same minus 2. Opposite uv, so u times 2, 2u. Positive plus 2 squared is 4. And then, again, now that we've sort of simplified everything, because one other thing to note about this if you didn't know, this second part never comes out any further. This part here is all junk, dead weight, and you never have to worry about that ever again. So anyway, once we have this, u minus 2 u squared plus 2u plus 4. We look on top. Oh, look, u minus 2, u minus 2. Those cancel out. And that was the one that was causing us trouble anyway. So now what we have is u squared plus 4 times u plus 2 over this thing, u squared plus 2u plus 4. And then we can just, now that we've gotten rid of that hole, we can plug in 2 and just plug 2 right in. So we end up with the limit of this. I'm going to put limit as u goes to 2 of this is going to be, we're just going to plug in 2. So we got 2 squared is 4 times 2 squared is 4. 2 times 2 is 4. 4. We got 8 times 4. 32. 4, 8, 12. And then you can just simplify that. 8 over 3, I think. So this one is a little bit more writing, but it's not more effort. Factor, cancel out the whole, plug in and get your answer. Same thing as the last couple. I'm not on the thing, probably not, that's why. Factor, plug it in, factor, plug it in. That's all it is. Don't overthink. Same thing here. Don't overthink. What is going on with this one? Oh my God. How do I simplify this? Well, this technically on the bottom is a difference of squares. X is radical x squared. Right? So the top isn't going to do anything, but you've got, and again, arrow instead of equal sign for all your thinking. And then on the bottom, we're going to factor it out. Radical x plus 9. Radical x minus 9. And now look. Factor. Same thing as before. It's the exact same problem as what we just did. And again, arrow for thinking. So now let's actually do the problem. The limit as x goes to 81. Now that we've simplified it down, let's plug it in. What's the square root of 81? 9, right? That's it. Don't overthink these. If you overthink it, you're going to panic. It's not difficult if you don't overthink. Just let yourself dissociate and do the problem. Here's a different problem. This is a different problem. This problem is not the same as the others. The reason is because we're no longer dealing with a whole in the same way. Here, at 9, we do get 0 over 0. But the way we're going to do this isn't by doing like a difference of squares, because we don't have a common thing from top to bottom anymore. What we're going to do here is we're going to rationalize the denominator. You've got that square root of x plus 7 minus 4. We're going to multiply the top and the bottom by the conjugate. X plus 7, instead of a minus, it's going to be a plus. And I'm going to tell you already, don't worry about the top. We're taking all this garbage that's on the bottom and just moving it to the top. Don't worry about the top at all. Just leave it there. It's all going to come out in the wash. What we're here to do is we're here to multiply out the bottom so that there's no longer a hole there. So once again, first, outer, inner, last. The whole point of multiplying by the conjugate is that all the middle terms go away. So it's just first term squared minus second term squared. So the whole bottom is just first term squared. Well, square root, it cancels out and you get x plus 7 minus second term squared. Well, what's 4 squared? 16. And then the top is just this ugly garbage that's up here. You don't care about it, just leave it alone. And then we go through and we can plug it in now. The hole has been taken care of. It's no longer a hole. So if I go through, I think. Yeah. Because here's why. X minus 9, radical x plus 7, all plus 4. Look what happens at the bottom. X minus 9, right? Well, looky here. Cancels out again. So look at what we're left with. The limit as x goes to 9 of, because the bottom cancels out, we no longer have a fraction, right? X plus 7 plus 4. If I plug that in, I'm going to get a number because I plug in 9. This equals square root of, well, what's 9 plus 7? Can I take the square root of 16? Sure I can. Right? And there's the whole thing. So once again, just like before, by doing a little bit of algebraic manipulation, here multiplying by the conjugate, we come out with a hole to cancel out so that we can just plug everything in and it's okay. So look, x plus 7 minus 16, right? Right here. What is x plus, so x you can't combine like terms for, but what's 7 minus 16? Isn't that negative 9? Yeah, cool. All right, we cool with this one? And again, the more you don't dwell on the details for some of these, it's easy, and then you just sort of rely on what your algebra is to be able to do some of these. Because the concept is what's more important here than some of the nitty-gritty details. What am I doing? I'm multiplying by the conjugate, simplifying. Then I can plug in. For all of these, our goal is to eliminate the discontinuity that's causing us the problem. Okay, new idea. So for all of these up until now, this it's the same thing over and over and over again. Uh-oh, I plug it in and I get something I can't work with. Let's fix it. That's all of these. With this one right here, we're no longer worried about plugging in and doing random stuff. Here, I'm telling you that it doesn't even matter what the equation is. It doesn't even matter what the function is. All I care about here, the limit I'm evaluating already. I'm giving you the answer here. If you've got a limit of p at -4, it comes out to 7. The limit of r at -4 comes out to 0. The limit of s when x is -4 comes out to -9. So here, look, limits, what's really cool about limits is you can distribute them no matter what. Plus signs, times signs, division signs, doesn't even matter. So look, I'm going to take the limit here, the limit here, the limit here. Well, what's the limit for p? Isn't it 7? What's the limit for r? Isn't it 0? What's the limit for s? Isn't it -9? So isn't my answer just 7 plus 0 minus 9? Isn't my answer just -2? Don't overthink this. Like literally, don't overthink this. Just plug everything in where it goes and then you're okay. You're going to want to overthink this. You're going to want to, well, what if it, no, don't overthink this. This is the easiest part of the whole thing. Same thing for this one. Again, this limit you can distribute for multiplication, which is not something that's normal. You normally can't distribute like that over multiplication. Here, because limits are easy, you can. It's great. Anytime that you've got a bunch of functions multiplied together, you can take the limits individually and then just put it back together. So look at the limit for p was 7. The limit for r was 0. The limit for s was -9. What's 7 times 0 times -9? Correct. 0, right? And then this looks weird, huh? It looks really weird. It looks really complicated, but guess what? It's not. Because again, what are you going to do? You're going to distribute this limit to the p, to the r, and the s. So what this really is, -4 times, what was the limit for p? 7. Plus 9 times, what was the limit for r? 0. Divided by, what was the limit for s? -9. So then we're just going to simplify. This is -28 plus 0, so I'm going to ignore that, minus 9 down here. And then I'm just going to simplify because the negatives cancel out. 28 over 9. If I presume they're going to ask for a fraction in simplest form, in which case you would give them this. But I'm going to tell you a secret about the AP test. You could leave it right there. On the AP test, if you stop here, full points. Once you've done all your evaluating and plugging everything in, if that's the answer you want to give them, they're stuck grading that one, and as long as it's correct, you're good. I'm not even kidding. Like, there was a good 5 minutes of discussion in my AP Summer Institute thing that I did in June about a question like this. And they're like, wait, so they don't have to go any further than this? No. If they stop there, full points. And if you don't stop here and then you screw it up, then you don't get the points. Even though this one is right, if you keep going and you screw up, they don't give you no points. So on the AP exam for the free response questions, stop here Make the AP grader earn their like $1,600 and free hotel stay that they get for grading your AP exam. Now, on the Math Excel, you will have to give them this answer because it's a robot grading it and they can't do things. But make the human go through all the work. I promise you, do it that way. It'll be better for you. Okay, I don't know why I made 2 copies of this. Who knows? Okay, it's the same thing. I'm just going to do it once. So here's the deal. In order to really get what's going on here, you've got to understand what's happening here. This one is going to happen often. Absolute value of something over the same thing. So this part, not including this part right here is always going to look like, when it comes to something like this, what you're seeing, let me make a vertical line. Let me make a horizontal line. Here's my axes. Let me make some tick marks here. When you're doing this, and this is gonna sound real stupid, but they do this all the time. If these absolute values weren't there, those would cancel out, right? X plus 4 over X plus 4, right? But here's the thing, they don't. So the deal of it is -1, -2, -3, 4. The deal is this: when we are working with this absolute value, this is shifted 4 to the left. At -4 and beyond, this is positive. Let me make this a different color. Make this blue. At -4 and more negative, it's a negative number. So the thing of it is, and then at the place where it splits, we've got our discontinuity. So here's the thing. If we're coming, this is a minus sign, right? Up here, -4 coming from the left, coming from this direction. Remember we talked about coming from the left. So the limit of this part is -1, right? And then the limit of x plus 10, now we can uncover this. Because remember, we're allowed to do those separately, yeah? This is the hard part. If we see this and we remember coming from the left, it's -1, coming from the right, it's +1. And then we come here at -4, we just plug that in and we get 6. So 6 times -1, right? So the answer here is just -6. Y'all see what I'm saying? So step number 1 is dealing with this fraction. As long as it's the same thing here, top to bottom, this is always the picture that we're working with. Coming from the right, coming from the left. This +4 just tells us we scooch it to the left 4, doing the translation stuff. If it was a -3, we'd scooch it to the right 3. But either way, they're always interested in what happens right here where the discontinuity is. So you know, if it's coming from the left, we got a negative. If it's coming from the right, we got a positive, yeah? And then this part, you just plug in normally. Don't overthink this. Don't overthink this. If you can have this picture here in your mind of the one here and the negative one here for this, everything else is simple as heck. Don't overthink it. Okay, these. So what I want to do before I talk about this specifically, did I do what I wanted to do and make more of those? No, I didn't, of course not. So we're going to put this off to the side for a second. We're going to talk about this in general. Sine of blah over blah equals 1. This is just a fact. We're not going to have the tools to prove this yet. We're going to have to go through a little bit more, and then the proof of this becomes very, very simple. When we learn what's called Hopital's rule, a French guy who actually bought the rights to this fact so his name could be on it. Not even kidding. That's what happened. He was a rich guy, kind of interested in mathematics, knew some people who were better at mathematics. One of them, a man by the name of Jacob Bernoulli, figured this fact out. And then the guy, Hopital, bought it from him. Well, what happened was he stole it. He found out that he was working on this, wrote the paper about it, published it, and then paid Mr. Bernoulli off so that he didn't get sued. That's how it went. So we'll talk about Hopital's rule later so that we can show why this is what it is. But for now, you can take this as gospel. Sine of blah over blah as blah approaches 0 always yields the answer of 1. Also, another one that is similar to this, not exactly the same, but similar, is cosine of blah minus 1 over blah also goes to 0. We'll talk about that later. But for now, we'll figure out just using this as gospel. We're not going to prove it yet. We're going to talk about why it is later on. But you can just sort of pretend like this is just a fact that just is. So as long as whatever's on the inside of the sign here is the same as whatever's down here, the answer is 1. So for example, I'm going to go ahead and erase this. I hope that's okay. Sine of 2x over 2x. The limit as x goes to 0 is 1. It doesn't matter what's in here. Sine of smiley face over smiley face. As long as smiley face goes to 0, the answer is 1. So the thing of it is, you have to make sure that what's here and here is the same. So like, what happens when they're not the same? What do? Let me show you. Let's say we have sine of 4x over 3x. I don't want that to be a 3 down there. If it's a 3, I can't do this problem. It needs to be a 4. So here's what you can do. You can say, forget that 3. I don't want it. I'm going to put it out here. Right? It was in the bottom, so you got to put it in the bottom here. I just pulled it out. And then all you have to do is put a 4 there. But now if I put a 4 here in a bottom somewhere, I have to also put a 4 on the top. So out here, you got 4/3. And then this whole thing, that's this, right? Sine of blah over blah. Hey, that part's 1. This times that. So your final answer is 4/3. Whoa. Okay, so let's do another one. So here's the thing. Once again, this isn't right yet. It doesn't look right. Let's fix it so it looks right. Yeet that 2. And then replace it with a 5. Well, if you put the 5 here, you're going to have to put a 5 out here too, right? So you yeet the 2, replace it with a 5, and look what you've got now. 5/2 times and then this part is just 1, and then you're just left with the 5/2. Ta-da! Don't overthink. If there's something wrong on the bottom and it doesn't match the top, yeet that into the denominator outside, and then replace it with what it's supposed to be replaced with, and then get your answer. So now that we've done all of this, I'm going to do this. Let's move this out the way, but keep it so that we have room. All right, you go over there. Now you come out here. So look, this doesn't match what it's supposed to. What's out of place in this picture here? Yeah, the 5, exactly right. So again, what are we going to do? Eat that 5. Now this is in the numerator, so it's going to be on top, right? But now, hey, now it looks like it's supposed to. We don't have to do anything else. So this part's 1. We got 5 times 1 is 5. And that's your answer. Don't overthink this. Don't think too hard about this. Make it look like it's supposed to. Throw everything else out. And then worry about that later. You know, you've got a little brother or sister who's trying to hone in on you playing video games. Kick them out. And then deal with them later when your mom comes stomping down the stairs to say, hey, no, it's okay. I'm done with this now. Now we can pretend to play video games. Okay. I think there's 2 more. Yeah, this one. So this one feels confusing. It's like, oh, wait, there's a cosine here. But that's a sine. This is a cosine. Yeah. Ignore this. This is, I don't know why they had this in there. But if I plug in 0 already, I'm good, because cosine of 0 is just 1. So this is just 0 times 1, which is, in fact, 0. And you didn't have to actually use this. Ignore that. If you get something like this, just plug it in like normal. Don't try and don't try and do anything fancy. This one's just a normal plug-in. Okay, we have we have a lot of time left, and the one that is going to take the most time to talk about is this last one. So I saved it to the end. When there is no other option, if you are like so lost on a problem and you don't know where to go, you have no idea what's going on with it, you're like so flipped out, there's one thing that you can always do. You can approximate your problem. So there's a couple towards the end that are called technology problems. And I'm going to show you using the graphing calculator I have on my computer. If you do not have, well, let me say it like this. I have a Samsung phone, an Android phone. There is an app called WabbitEmu. I'm going to type it in here. That you can just download, and it is an emulator for a TI graphing calculator. I recommend the, what is it called? The 84 Silver Plus C or whatever. I recommend that one. Here, I'll show you what I'm talking about. I recommend this one. This is the one I use on my computer. If you have an Android phone, you can just download this app and you just tell it to get the appropriate ISO file, and it'll find it and it'll put it on there. And then you'll have a $150 calculator on your phone for free. Yay. If you do not have a Android phone, if you have a computer that's either Windows or Mac, or even I think Linux, not a Chromebook, unfortunately. I've been trying to figure out how to do it on a Chromebook, and I can't. But if you've got like a normal computer, you can download this program, and I've got all the stuff. I'll share it in the Google Classroom in a bit. The only other program that I could recommend is Desmos. Desmos, the graphing calculator, is a really, really good one. If you have an iPhone, you can use Desmos. If you need a scientific calculator, Desmos has a okay scientific calculator, but Desmos is really much better for the graphing calculator stuff. So we'll do this. I'll show you this on WabbitEmu, and then I'll show you this on Desmos. So let me present in a way that's going to be less of a pain in the butt. Okay. Hopefully everybody sees this. Okay, so when you have no other choice, like here, you can't simplify this in any way. Not really. So what you can do is you can type this into a graphing calculator. You're going to go, let's see, x squared minus squared minus 1, all in parentheses. I've got to make a parentheses here. Somehow. x squared minus 1 divided by, oh, where are you? Math. There's an absolute value thing here somewhere. There it is. Absolute value of x I need to have parentheses here too. Of course. Math 1 absolute value of x minus 1. You type this in and you can actually make the graph in your calculator. Now we want as x approaches -1, and let's do our min for x is -2, our max for x is 0. Let's scale it, I don't know, 0.5. Why not? Let's be saucy. Our y min not going to be very big. Let's make it like -3, +3, and you'll be able to play around with this and see what's going on. And then what you want to do from here is hit the trace button, not graph, but trace. So we want to figure out as x goes to -1, what happens, right? If I try and just plug in -1, it gives me an empty thing here, right? Because it doesn't know. But what you can do is you can use the points approaching -1. So like if I wanted to do -1.1, that'll give me the answer, right? That had better be 2.1. Let's do -1.01. We're getting closer and closer and closer to 1, just to see what happens. I'm going to type in 1.01, -1.01 for x. Now my y is getting even closer to a certain number. Let's do -1.001. And the point isn't to just keep going for a while. You're going to notice a pattern. See how it's approaching 2? That's on purpose, right? So, you know, we keep going and going, and it's approaching, and it's approaching, and it's approaching. We're getting a pretty good idea of what's happening, right? And then the same thing, if we go from the other direction, the other side of -1 is -0.9, -0.99. We're getting closer from the other side. Just being careful and seeing what happens. And look, it's pretty clear, I should hope, it's pretty clear to see that the answer, if we got closer and closer and closer and closer and closer, still is going to come down to 2, right? So we can be pretty sure that this is going to be about 2. So now if we look here with part B, they're asking about what the graph looks like. And again, this is just sort of to help train you on the using of your graphing calculator. And so it tells you that the x window is -2 to 2. let's change the window so that it matches -2 to 2, and it tells you that the y on the scale here is 1. Let's make everything match what it's supposed to. The y goes from 0 to 3, and it's just they're just telling you. And the scale for the y is 1. And now if we just hit the graph button, it's asking you, hey, which one is in your window? Yeah? And if you look, which one's in your window? Well, it's not this one. That's a parabola. That's not right. This one's skewed to the left, so that's not right. This one was skewed to the right. This is the absolute value V shape is dead center, so it's not D either. And if we look, it matches, and we get the correct answer is C. And the only thing that from here they're going to ask you to try and confirm it algebraically. If it comes out to like a square root, it's going to be clear which square root you're coming towards. But like here, it's just asking you the same thing again. Okay, so this is my version of this problem. It may not be exactly the same, but it is going to be reasonably close. I'm going to zoom the picture in a bunch so it's easier to see. The statement, the limit as x goes to 0 of f of x exists is it false or true? Well, let's look. X goes to 0. Do they come to the same place from the left and the right, Luke? Yeah, so does it exist? Yeah, right? So, true. The statement, limit as of f of x as x goes to 0 equals 0. From both directions, do they both go to 0? So it's true. And so that's the question that you're asking. Is just, is that where it happens? Is that where it goes? The statement, limit as x goes to 0 of f of x equals 3. Well, when we go here, do they go to 3? No. So false. At 1, is the limit -1? Do both hands go to -1? No, this one does, but in order for a limit to exist, they have to meet. They have to come to the same spot. Here, they don't. The left-hand limit is good, but the right-hand limit doesn't go to that spot. So we know that that's not true. Same thing here. It doesn't go to 1 either. The right-hand limit goes to 1. The left-hand limit doesn't. So that doesn't work. The statement, limit f of x as x goes to c exists at every point c from -3 to 1 exclusive. So what we're saying here is we're not focused on the endpoints where we know it doesn't exist, but every other spot, does the limit exist? Does every other spot have both arms from both directions coming to the same place? Yeah, so true. The key here is the parentheses mean that the endpoints aren't included in our search here. We don't care about the endpoints. The statement, the limit of f of x as x goes to 1, so we're looking at 1, does not exist. So either they meet or they don't meet. If they do meet, then the answer is true. Then the answer is yes, there is a limit. If they don't meet, then the answer is limit does not exist. So limit exists, yes or no? No. So the limit does not exist, which is what they said. So this is, they're trying to talk in circles, right? The statement, the limit does not exist, that's right. That is the correct analysis. And so the limit does not exist is yes. The statement f of 0 equals 0. So now they're not asking about a limit. They're asking, hey, plug in 0, what do you get? We don't get this, right? We get this dot up here, yeah? So f of 0 gives us 3, not 0. So it's false. You see what I'm saying? And then here, this is what we're talking about. F of 0 is 3, which is true. F of 1 is -1. So let's look. At 1, where's the solid dot? Is it at -1? Is that an open circle or a closed circle there? It's open, so it's not there, right? Okay. Bye. Class ended 2 minutes ago. Bye, everybody. But yeah, so Luke, the dot goes here. So it's not -1, it's +1. So that statement is false. The statement f of what? This is a long problem. I'm sorry. Statement is 1. Yes, that's true.